Hi, I'm Professor Usaki. Before we start the lecture, there are a few things that I need your help. First, please mute your microphone most of the time unless you are asked to provide your feedbacks or questions. Second, if possible, please use a headphone or earphone instead of a speaker to receive the best voice quality of the lecture. In addition, using a headphone also helps us to avoid the echoes when you are expressing your thoughts. Finally, this is an interactive class. You may be asked to answer a few pop-up questions during the lecture. Please pay attention to what's going on right now. Thanks for your cooperation. Now, please sit back, relax, and enjoy the lecture. Good afternoon. So today we are going to talk about sequential circuits, which is another big category of the digital circuits that in our logic design that we will interface. But before we start talking about the digital sequential circuits, there are definitely some of the leftover, but also I think valuable stuff. We have to talk about floating points. So not sure how do you spend the time of quarantining at home, but for me, well, definitely, right, these days we see a lot of business they are having trouble with, but there are definitely some other business that take advantages from. So one of the big winner I thought is probably Netflix. Like in the past of my life, I never thought that I want to subscribe to Netflix. However, because of the quarantine at home, so I have a lot of time that I don't know what to do. Then, well, I would go up and go to Netflix to search for something that I'm interested. So, but you know, in addition to the new things, Netflix, they try to pull up some old things. So not sure how many of you heard the song Fly Me to the Moon. And that was the song that we played just before the lecture begins. And it was actually the ending scene of an animation called Neo Genesis Evangelion. So if you are familiar with the history of Japanese animation, it's basically a very, 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 very iconic work in the Japanese animation history. And well, I mean, it has a lot of like very important meanings in Japanese animation industry. However, one thing I do, if you are interested, definitely go ahead and look at the like watch for the animation when you have free time. But one thing I do want to tell you is that don't try to understand what it is talking about. And well, there's a reason why I played Fly Me to the Moon. You will know later. Well, but before we start, we should talk about something we learned last week. So we spent a lot of time talking about number systems, but from my personal experience, none of the previous class in computer science or electrical engineering were ever talk about how to, like why we have floating point and what are the other options, what are the limitations of floating point. And it turns out that there is a misconnection there's some misconnection between misunderstanding, maybe that's the right word, misunderstanding between programmers and the hardware. So in many cases, we create a lot of bugs in our programs, but not because you guys are not a good programmer. It's just because you don't understand this is how the hardware works. So so in our lecture, I think it's a good chance, since we are going to talk about the ALU design, the adder. We talk about the ALU design, the adder design. So it's a good chance for us to figure that out. So to express relational numbers, integer and fractional parts, we do have two different frequently used expression. One is the fixed point, and the other is floating point. However, fixed point, because it's a floating point, its decimal point cannot move around, so it has limited range that you can express the number. And however, for computer systems, we always want to express as many as larger range as possible. So that's why we use the floating point design. However, there is a limitation in the floating point design, is that think about, we only have 32 bits, but we want to express numbers with a large range. And it turns out that there are numbers that you cannot map into the floating point number space. So one of the examples that I show here is that 0.004, which you think is a simple number in decimal. And if you use a fixed point, you can definitely express this number precisely. However, if you look at the graph, the calculation that I draw in a button, and it turns out that this number needs a lot of not a lot more digits than the 23 digits that's provided here to express. So you can only capture the number at until this part, but not afterwards. So you think you store 0.004 in IEEE 754 floating point numbers. However, it's not that number you sought. So that's why when we are launching the sample code, it turns out that you are going to get a different number than you were imagining. So that's one of the drawback of floating point numbers, is that you will lose precision. And in addition, some of you have the misunderstanding, well, because the range of floating point number is larger than integer, so it must be able to express more different numbers than integer. But the answer is no. So the reason is because, first of all, they all have only 32 bits. So the maximum number that 32 bits can express is just 2 to the 32. And in addition, in the IEEE 754 float format, there is a huge number. There are a few spatial numbers that further reduce the distinct numbers that the number system can express. So for example, they have +0. They not only have +0, but they also have -0, which we have been criticized for as a reason why we want to complement in the integer expression. And not just that. So infinite number, we also have like plus and minus version. And for not a number, it's even worse, because everything with its exponent as 255 is another number. So no matter what's afterwards. So it means that any prefix with this is right now, scrapped from the number system. So obviously you can express a lot fewer numbers than the integer. So and the other thing is that that's just not the number system, right? So we talk about like for our C code, well, this loop end. And for the integer version, because the sign calculation is part of the LU. So when you calculate the number, we share the same hardware for unsigned, signed integer. So and the plus or minus sign is just part of your calculation result. So we have a spatial situation called overflow that would cause your most significant bit to be overflown to the sign bit. So it turns out that if you are adding something to the maximum number in the integer, then it will become a negative number. So that's why this X loop will finish. However, for floating point is not the case, because if you look at the floating point adder, the sign calculation is actually separated from the LU calculation. The LU only take the exponent and the fraction and calculate the difference in their exponent and put the result in a big LU. And finally, have a separate circuit to calculate the sign. So if and the calculation will tell if this is if these are two positive numbers, they would never give you a negative result. So that's why we spend. So that's why in the previous code, if you are having y if you are having these pieces of a code, it will never end. And however, there's one more thing that's interesting. That's one more interesting, which I think Fox has a pretty good discussion with me by the end of the lecture. But I think this number, after I have done some more research, I just figured out that, I just accidentally created a very good case for explaining some more errors that would occur in floating point numbers. So it ended up that the program will finish since I is always a positive number, which is about like 17 million. So I don't think any of you, I don't think many of you have tried to think about why we stuck at this number. So I think it's a good time for us, given that you now know the IEEE 754 format, you also know how the LU is designed. Can we spend some time together to think about why this code will stuck at this number but not incrementing anymore? Okay, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so let me share the result with you. So looks like a lot of you think C is the right answer, but can I have someone explain why you think so? Raise your hand, raise your hand. So 19 of you think it's C, right? Can I have any of you try to raise your hand or at least express your thoughts? Okay, I have Tyler.
Okay, hello.
Hello, I can hear you.
All right. So, well, we can cross off D and E because it's. I mean, it wouldn't be stopping there. Like if you add one to a number, obviously it would increment, but it doesn't. So there has to be something that's happening there. And in that case, we could also cross off E, because if you add anything, it should be going up, but it doesn't. So of course something's happening. There, like now for why it's not A and B, there's no condition that we were given that this specific number is special with what we've learned so far. So like it can't be it's a special number like infinity or non-number. And let alone that we haven't even heard of like that special number that's just treated differently where it just stops. So it's only logical that it's just the maximum number that we could ever reach.
Okay. But okay, if we go back to the IEEE 754 54 format, right? How many digits are there in the fractional part?
23.
23, right? So you have 23 here, and we say it's always 1 point F, right? So F is 23, so you have 24 bits, right? So if you have 24 bits, what's the maximum number you can express with this 24 bits?
It would be 2 to the 24th, right? Or like whatever that number would be that you could reach. Well, no, it would be 2 to the 24th. No. 2 to the 23rd, I think, because you have to remember, like there. No.
Okay, so if you have 32-bit integer, right? What's the biggest number?
Oh, it'd be 2 to the, well, it would be, it would be like pretty much, okay, it would be, oh geez, it'd be 2 to the, oh my gosh, my math is like messed up today. It's like 2 to the, if you have 32 bits, it'd be 2 to the 31. Well, no, it's 2 to the 32 minus 1.
It's 2 to the 32 minus 1, right? And so for here, we would get at least 2 to the 24 minus 1, right?
Yeah.
If everything here is 1, right? But don't forget, there's one more thing, that's exponent here, right? So you can actually have like 127 times 2 to the 127 here, right? So so one thing you can tell is that 2 to the 24, 2 to the 24 minus 1, they are definitely not the maximum number that the floating point can express, right?
Yeah.
And I can also give you a code example. So, well, let me see. Well, let's just write Python. Python's not a good example because it's not. Let's see. Okay. So if today I change the code here to be I plus equal to 2, right? If that number is the largest number, right, you are going to stop at 16 million, right?
Yeah.
Right now, let me run this LLDB, which is a profiler. Doesn't affect the correctness of your program, and I keep running it. And right now, let me stop it, and let's print I. Right? This is a number, and is it smaller or bigger?
Bigger.
Right? So that is, C is definitely not an answer. Okay. So if C is, okay, thanks, Tyler. You give us a lot of insights. Okay. All right. So if C is not the answer, then what's the answer? Okay, Fox, what do you think?
Hi, can you hear me?
Yeah.
All right, cool. So the answer is D.
Okay.
And it basically what's happening is if we look at the floating point format of the numbers we're adding, we're actually going to notice something very quickly. We will notice that the difference in the exponents of the two numbers is greater than the length of the fractional section, which means when you actually go to do the addition of 1 plus that number, the bits won't line up. the bit that forms the 1 will fall outside the range of what the fractional area covers for that number. When you attempt to add 1, it cannot increment because the addition isn't getting processed out that far. Basically, or actually, no, let me reword that. Let me reword that. That came out wrong. Basically.
So what if you listen to my explanation and graphical explanation on this and see if you agree with me? All right, so we want to mention that. All right, so one thing I do want to mention to you guys is that, well, when you are writing your program, you have to understand how your hardware works, right? So the thing is that, right? I think Fox is getting almost exactly 100% right. Right. So the thing is, right, if you look at the design of the floating point ALU, right? So we have two numbers, right? Say we have two numbers, right? One is the 16 million one, and if you convert it to binary, you will figure out it's 1.0 times 2 to the 24. So if you write it in the IEEE 754 format, is actually like this. So you have your exponents part, you have your fractional parts, and the fractional parts are all 0 because we ignore the leading 1. However, for what's 1? So 1, right? 1 is 1.0 times 2 to the 0. That's 1, right? So if you write it in the IEEE 754 format, this is what exactly likes. So their fractional parts are all 0s and the leading ones are all ignored. So that's okay, because this is what a number system it is. However, what really happened is that if you fit both into the floating point ALU, right? Like, let's look at that, right? So you will have a small ALU here, which try to calculate the exponent difference. So what happened right now is that you will figure out you have to shift 24 bits because the difference is 24 in their exponent, all right? And here's what happened, right? So if you have one leading 23 zeros after shift 24 bits, it's 0, right? So you are essentially calculating 1 with 23 zeros shifted by 24, and you got 0. And with this, so you are always adding 1 times 2 to the 24 with 0. So that's why the floating point ALU is doing its own job. But the thing is that after the exponent difference, the 1 is just so small for us to notice the difference, right? So I was thinking about what's an analogy. So one thing I saw this weekend is that, okay, if I have $16 million, $16.7 million, right? Do I ever notice that I lost $1? The answer is probably no, right? So one thing this slide tells you is that, okay, if you reach a point that you have 16 million bucks, right? You don't need to earn more. If you earn more, well, donate it somewhere. For example, your poor UCR, right? So we can get more buildings, right? But the biggest takeaway here is that, you know, in floating point, if you are adding a big number with a very, very small number, there is a chance that you are going to lose precision and make your result forever wrong. So thinking about if you are writing a banking system, right, and you have well, 16 millionaire, right? He wants to just deposit $1 inside his account, and you use floating point to store his deposit, and it turns out that he will never get this $1 deposit, the $1 deposit, right? And you might think, well, this is a hardware bug, right? However, no, this is no, because this is what the LU it is, right? And so because this is the hardware nature, so some of you think about, well, this would raise an exception, but the answer is no, because this is what the LU should act like. And in fact, this is what the IEEE 754 would tell you to implement your LU. So it's even worse because your program would never notice that there is an error in your result. So sometimes it's really important, a good programmer needs to know this kind of hardware features to avoid bugs. So a lot of people who doesn't understand the computer science, they will claim this is a hardware floating point bug. No, it's not. This is a completely software bug, and it's erased by the fact that the programmers doesn't understand, right? So Fox, do you have anything to add, or are you satisfied with my explanation?
Oh, I think one more thing I wanted to say is just to add to this is that you should never look at floating point numbers as a accurate way to represent numbers. Think of it like accept it for what it is. It is a discrete floating point finite state number system, but there are methods you can use to make great use of this kind of number system. You just got to be a little more careful.
Right. So that's also another reason why we need some kind of a number system like fixed point, right? Because fixed point, at least it can evenly distribute those floating point, those decimal point numbers in its number space. But in floating point, that's not really the case, right? So being a programmer, always remember, if you want to use floating point or even other IEEE 754 point, then you have to take your own risk, and you have to always be really careful about this kind of precision loss. And another follow-up question that I want to ask you, can you think of other example that would result in the same situation? So Fox, do you have anything in mind?
What kind of situation? Like, oh, these kind of weird hardware bugs?
Or similar to this, just similar to this, is 16777 to 16 the only spatial number that would cause this situation?
No, it depends entirely on what you're adding to the number. But
right.
It's you'll probably see the special marks at the powers of 2, because that's when the most significant bit of the smaller number falls off. At least that's what I assume happens. I haven't tested this.
But I would say it's probably whenever you see two numbers, their difference is exactly or even more than 24, 2 to the 24.
Yeah,
right?
When their
there
ratios
is
are
a chance, right? Then your ratio is larger than that, right? This is what you will get, right? So if we look at, right, like this code, which I just modified, why it stops at 33, 55, 44, 32, right? Because I add 2 this time. So if you do the math, you will figure out this number is actually 2 to the 24 times larger than 2, right? So this 16 million is not the only spatial number that you should remember. In fact, anything with their difference, like this 2 to the 24, 2 to the 25, 2 to the 26, in floating point number system, you are going to meet exactly the same situation. So a big takeaway here is that, okay, if in your application, you need to add a big number with a small number, floating point is definitely not some numbers, and you really want this to be calculated precisely, then floating point is definitely not the number system that you are going to pick. All right? Okay, so I believe this is a good example for you to learn. And what if we go to a next example, which is also the loop. And right now, you can tell the difference is that I change the code that I use in while. But can you tell me, what do you think the execution result of this program will be. Question?
What if I accidentally picked the wrong one? Like, was it like
you mean
on the pool? I accidentally picked A. I'm like, no, wait, I didn't mean to.
Oh, that's okay. That's okay.
Okay.
That's okay. I don't know if Zoom allow you to like roll back, but I don't know.
Okay.
That's okay. We are not judging you if it's correct or not. And sometimes I like you guys to be wrong in the first round so that you will know, I don't know this thing, right?
Okay.
All right, let's wrap up in 15 seconds. All right, 5, 4, 3, 2, 1. Time is up. Okay, Giovanni, since you are already you already identified there are potential answers that you may make wrong. Oh, by the way, let me share you the results. So right now we have both 36% on C and D. So Giovanni, what do you think? Do you mind to share us?
I thought it was C.
You thought it's C, but why?
Yeah, because if you just kind of follow the program, it looks like I would never get to 0, so we just keep incrementing, and then go back to I. So I just think it will never finish since there's always going to be positive non-zero number.
Okay, so so you think it's a number, right? You think it's a number, right? But first of all, okay. So okay, thanks a lot. Okay, Michael, what do you think?
All right, so this is like one of the things I'm not totally sure on because I've never had my code do this. But if I remember correctly, so okay, so first off, let's look at the code. The code, we're doubling I every single loop. Doubling I means we're not changing the fractional section, we are changing the exponent section, basically increasing it by 1 every time. So there comes a limit.
Yeah, but the reason why I use plus to double here is because we haven't talked about multiplier, and I think it's unfair to do multiplying here. And the other thing is that the adder design and the multiplier design in floating point are again different. And as you said, for multiplying, we are modifying the exponent directly, probably. But
doubling
is
a special case.
Right.
I'm willing to consider doubling a special case because of the sheer number of ways you can implement it.
Okay.
So in this case, we're doubling somehow. I mean, you're adding I to I, so I is now twice what it used to be. But this means that every single time you double it, you're going to increase the exponent by 1. You will eventually get to the point where you overflow the exponent. Now, IEEE doesn't allow the exponent to overflow because that doesn't make sense. And so I believe what happens is that the floating point processor at this point would return positive infinity, but it could also be not a number. So I don't remember which one it was.
Like, okay, if nobody knows, right, the best way to do it, right? Let's test it, right? You got let's test it. So this is, I believe, I have a loop flow to revisit it to the C, right? Okay, right. So here I am doing I plus I, right? Or I can do equal to I. So you feel like, yeah, it's the same code, right? And let's use, again, GDB-like tool to run it. And float, revisit it too. Woohoo, let's run it. Okay, did you see we are done? We are done. We are done. We are not done yet, right? And because this is exponent, so we expect number to grow rapidly. So yes, you are right. We got into plus indefinitely. So that's a spatial number, which I already saw tell you in the very beginning, right? It's a spatial number that defined by IEEE 754. And the trick is that if you are adding anything to plus INF, the result will always be INF, right? So that's why we stay at this number. All right. So so that's interesting, right? So let's see more, right? So for this one, right? It will end up with some spatial FP32 presentation, and that thing is this one, the plus INF, right? And if you have your number reaches plus INF, it will go to plus INF forever. So now some of you might ask, okay, what about not a number? So not a number is when you are doing things like 0 divided by 0. So it's by no means some meaningful calculation mathematically. Then the LU would capture that and put not a number there. And when you first reach not a number, your system will raise an exception. Okay, Michael Fox, anything to say?
Yeah, I wanted to add one thing. You guys probably noticed that for not a number, there's multiple numbers that are allowed for it, where all the X's. That's called the payload. And the payload is not generally used, but some engineers, back when the standard was first introduced, decided that it would be cool in 1985 to allow floating point numbers to carry arbitrary data for signaling reasons. In case you were curious about why it was designed that way. It's not used, but it's capable of it. But that's actually was another reason why not of numbers were supposed to be a thing, is that you were supposed to be able to encode data into floating point numbers for error signaling for, like, I don't know, when you did more complicated math. Because we were thinking at the time, what if we made a circuit to calculate trig or other functions, and we'll want to use floating points more? And I don't know what they were thinking, man, but this is what we got.
But this is also the world that we are living, right? So being a programmer, you definitely have to know this. All right. So thanks for your comment. And right now, well, let's go back to another question that we have in a demo last week. Is that, well, some of you were asking about, okay, so, well, for this number, right? We said, well, for 0.004, we cannot express that in floating point correctly, but can we get it, can we have the result correct at some point, right? So there are more floating point things that we can talk about, right? So first of all, in IEEE 754 was introduced, there is not the 32-bit is not the only format. They also come with another different flavor that's called 64-bit, and it uses a word double to describe this floating point format. This is called double precision floating point format. But don't be fooled by the word double, because it double means that it just used twice more space than 32-bit to express a number. But if you look at the exponent, it's only 3-bit long, and but the fraction part is significantly improved from 23 to 52. And if you convert it to decimal number, right, with 32-bit floating point numbers, we can say roughly we can get a number with seven, like a number after 7 decimal points. We can capture most of the behavior like that. However, I already give you a counter example, right? Like this one, it cannot. It's only 4, but it still doesn't work in 32-bit float. But this is just an approximate. So you can assume that, well, in most of the cases, if you want to express a number that you have at most like 7 digits after the decimal point, you could say, well, I want to use a float, although there are still examples like this, right? Or this one, right? And for 64-bit double, right, it's approximately 16 bits, and the largest value, as you can tell, it could be as large as 10 to the 308, this big order, right? So this is so it has a larger number space because we use 64 bits. So let's revisit the demo. So for this this program that we had in the last lecture, the only thing I did here is change the float to double, and print. Well, for printf, you need a different format, right? So let's run the program and see if the double help us to resolve the issue. So I believe this program is that precision 2. No, precision 3. Okay. Okay, so right now I have a precision 3, right? So if I run the precision 3, right, then one thing you will learn is that, wow, now with double numbers, both results are right. However, I do want to comment on this one. I don't think the 0.2 result is correct in a way that I think that just because there are some rounding expression in the C programming language. Because if you do the same in Python, right? So for Python, they would by default use let me see. Where is my float Python? Okay, so for Python, they would by default use double precision numbers to express numbers. So if I do this, right? If I do this float.py, you will see, hey, this is what we exactly get, right? So so 1.2 is not something we can express even in double. And for C, because the printf did some rounding, so you see 1.2. However, that's not actually what it is, right? So and Python shows you this. This is not exactly the number, even though we are using double, right? So double does a better job in at least making the difference smaller, is more precise. However, this example show you, even for number like 1.2, it's still not something you can capture with double. Okay, so let's do this loop again, right? I believe that's the last round, very last round for this question. What would you see? All right, let's wrap up in 15 seconds. Five, 4, 3, 2, 1. Time is up. Okay, I bet some of you must saw the accident for animation. So, well, sometimes, the making slides is tough because you have to make the order of animation correct to not making you guys feel less fun about the question. So, but okay, so looks like the answer is D, but can some of you tell me why? Why it's D again? Why the answer is D, staying at some positive number. Okay, so Fox, I know you raise your hand, but but I know you know the answer, but can I have somebody else? If not, I will still want Fox again. But in the meantime, I want to make sure the rest of the class get it. Can I have someone else? Is Fox the only friend of mine during this class? Speak up, speak up, speak loud. Okay, looks like I only have Fox. Can you share?
All right, so basically pretty much the exact same thing happens as with the float, because we haven't fundamentally changed how we represent our numbers. We've just added more bits to it. So we have more space to play with, but the structure is still the same. So you're still going to get the exact same effects.
Right. So you still need to calculate the exponent difference, right? And we have one number as 1, but at some point, right? If for this guy right now, the threshold just increased to 2 to the 53. Right. So one demo that I could give you here is that, let me have the loop double. All right. Revisit the C. Okay, well, because we don't have a lot of time, and this is a big number, so this is actually 2 to the 54, I believe, and right now that's assume that our number is already fast forward to this number, and and then let's run it, and let's plus 0 with it, and what would happen is that if you run loop double, well, let's just use LLDB. I think it's easier. Loop double, revisit it, right? Let's run it. Okay, right? So, well, if you're interested about what's printed here is actually a program, a part of the program to dump what's currently in the memory content of that number. And if you learned your CSE 61 carefully, you will notice that, well, because in SAD6 we use little endian to store numbers, so the arrangement of this bits are different. So, but if you print a number right now, right, like let's print I, right, you will see, right, this is exactly the same number we just assigned. So because the difference of these two numbers, they are too bigger than both LU can capture. So adding 1 to that is actually like a no up. Not because the LU is not doing anything. The LU is doing its job. However, they are, for some reason, they are shifted right, become 0. So you would never see the number incrementing. So you are starting at some positive number, and that positive number is not a number that would cause exceptions. And in fact, your LU is working fine. It's doing its own job. Right, so that's what's happening here. All right, so that's let's see. So all right, so that's the double number, right? So we know that double provides us more precision, and in many cases it's a lot better than the floating point. However, you think we are going to add more precision into our number system, but in 2008, IEEE, since it first announced IEEE 754 after 1985, well, since 23 years, the first addition to this standard is adding a half floating point type, which only use 16 bit to store a number with decimal point. So you thought, well, isn't the human beings trying to move forward to a situation that we want more precision? But how come we start to add this new format in there? So I want to encourage you to think about the reason why we start to have this floating point number. Okay, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so let me share what you guys think. So according to our poll, 61% of you think is C, but because this is a question that asking how many of the following statements are possible, so I want to have some of you to tell me what are the two that you agree with. Okay, I have Sahas. Okay, finally, someone else.
I'm not entirely sure about it, but I think one of them would be using less precise data types to allow the hardware to support more applications, because having a 16-bit representation will allow more memory to like be used elsewhere.
Okay, so how many of you chose?
Oh, I actually chose D, but I'm not sure if that's accurate.
Okay, but what are the options that, well, what are the statements that you agree with?
The other two was using less precise data types allow the same number of transistors to deliver more results simultaneously.
Okay, why that is correct?
It was more of like an educated guess kind of thing, because I thought if we're using smaller representation for the data type, we can have the other transistors that aren't holding, I guess, the 16-bit data to also have another additional 16-bit, which allows, I don't know, like faster calculations or something like that.
Right. So the same. Okay. So the first statement, right? We are talking about the same number of transistors, right? And previously we have been talking about like, okay, if I want to implement an adder, right? How many transistors that I need, right? So so this is kind of like another way to ask about your understanding about the relationship between the amount of data you need to process and the cost of transistors that you need to implement support for such data. So if you have 32-bit wide adder, as you learned before, then your adder is twice as large as the 16-bit, right? So you get it right in a way that, okay, if I only have this amount of transistors, and if I only need to support or given this amount of transistors, I can use this amount of transistors to implement more adders in a way that I can process more numbers at the same time, right? So that's why that's an option. And how about the second one? Can we use less precise data types and numerical methods to reach the same precision with shorter latency?
I don't know about that one.
Mm-hmm. Okay, so for this, I would put a no, because the reason is because, right, like for well, first of all, right, the reason is that if you want to reach the same precision, right, you must guarantee that there is nothing loose during your calculation. But unfortunately, when you convert a number to float 16, you already start to lose precision, right? So that's never possible.
Mm-hmm.
Agree? Okay.
Yeah.
So let's look at the three which you are not sure about, right? So, okay, Michael, do you have anything to add?
Okay, so I was a little on the fence for option 2. There
Mm-hmm.
are algorithms that
Mm-hmm.
compute certain kinds of floating point problems by breaking them down and having smaller data types to solve a particular problem algorithmically can actually end up being much more efficient than trying to throw larger data types at the problem. I can't think of any examples at the top of my head of doing this, but I was a little iffy on the wording of the option. So I thought maybe it could apply.
So this yes or no. So one thing I want to say is that it only applies in a case that your result register is stored in a format that is twice as wide as your data type. You can prevent the precision loss when you are operating on two big numbers or two extreme numbers in your small number system. You know what I'm saying? So it's not, it still relies on the hardware support to achieve that. So for example, well, we will talk about that later. Well, we can probably talk about that later in other classes, but to be sure, what you said is not generally true unless the hardware intentionally provides support for that.
Right.
So for example, it works on x86 because for x86, your floating your register is already 64-bit long, right? So you can definitely do it. But if your LU just have a 16-bit register, then it's not going to happen.
Right. Okay. Okay. Yeah, I see what you're saying. I was thinking.
Okay.
I was thinking of using smaller data types to represent like larger pieces of data. Like it's a super. I think it's called superscalar processing, where like you just break down the problem independently and send the little chunks off to different processors and get the data back.
No,
it's not
that's
that.
not.
All right.
No, that's not. No, that's not. Yeah.
Okay.
But if you are interested, okay, if you are interested, you can stay at grad school. You can take my CS203 next quarter. No. All right. It's not too late. It's not too late, by the way. Okay, so if you are interested, because I know we are short on students for the upcoming fall quarter for grad school. So if you're interested, you can apply for sure. All right, but okay, thanks. All right, so okay, so but let's keep working on Saha's issues, right? So okay, so well, Sahas, what is that?
It's the UCR logo, Scotty.
Right. So, but can you tell the difference from the left-hand side to the right-hand side?
The right one's more pixelated than the left.
Right. But okay, so here's the thing, right? There are applications that we can tell it's different, but we can still know what the context of it, right? So there are applications they can tolerate the loss of precision, but if you look at the whole applications that we have, so this is a 737 MAX airplane, and many of you already knew that before the COVID-19, a lot of this type of plane, well, this type of plane is already grounded because the software is not precise enough to handle a certain situation, right? So good example that airplane software cannot tolerate precision loss. And for this, okay, Michael, anything to add?
All right, I hate doing this, but I like planes a lot. I am a very big fan of planes, and that is most certainly not what happened with MCAS. That is certainly not what happened with MCAS.
Okay.
That was bad design pinning an entire safety system on the function of one of two angle of attack sensors. In fact, the MCAS system was hardwired to use one of the two redundant quote unquote sensors. So if the main MCAS angle of attack sensor failed, you wouldn't even know because the warning light to tell you that they disagreed with each other was optional. It was a giant engineering mistake. The MCAS issue didn't come as a software issue. It was like an overall design disaster. It's just that they patched it in software.
Okay. So the thing is that well, because for the early report, it points to the software errors. I don't know, is because of the Boeing doesn't want to concede that they made a mistake in their design. So what they keep saying about is like, okay, our design is fine, the hardware is okay, it's just a software issue, right? So that's why I'm saying things like that, right? And I don't know if a later report updated that, but not from the perspective that I have been reading. Okay.
Yeah. It's a complicated issue.
Yeah, I know, and I'm also addicted to this kind of airplane things, and I do have if you get a chance to visit my home, which you definitely should not do it right now, I do have lots of this plant models in my room. All right, so let's talk about that later, but that's get resolved. So one thing we are on the same page is that there are cases that you cannot tolerate precision. So in this way, Sahas, do you think using floating point 16 would enable more applications or reduce applications?
In the current scenario that we're talking about, or in general?
Yeah, like in general.
I think it should increase it, right?
Okay, so another thing I can tell you is that, okay, if I have a program works in floating point 16 but cannot work in floating point 32? right? So the thing is that floating point can only work for a subset of floating point 32 application, right? So in
Right.
this way, are we enable more application or fewer applications?
Then no.
Okay, but the reason why we added the 16-bit format is just because, okay, so Mike, Fox, what do
Wait,
you want to add?
sorry. Wait, so are you saying that for that question, the fourth option is not applicable? Because they just added an additional data type. They didn't remove support for previous ones.
Right.
So,
well, but the thing is, no, depends, because there are hardware that only support 16-bit now, which I'm going to talk about.
oh, as in, oh, there's hardware that only supports 16-bit.
Right. Okay.
Oh, that's what you're talking about. All right.
Okay. Okay. So the thing is that, right, not all applications require high precision. And as many of you know, that machine learning is one of the top, like the buzzword that everybody is talking about, no matter you know it or not, you must claim that I know neural network. What is that? Otherwise you won't get a job, right? But the thing is that you think neural network needs a lot of computation. That's true. However, they don't require the thing to be very precise. So I would say only 1 and the 4s, they are correct. And there are examples like that. Okay, so for NVIDIA's latest Turing architecture, they do add support for mixed precision, like FP16 and FP32. However, if you pay attention to their design, those mixed precision, they may not work together, and you have to declare what kind of math mode that you are using. But the thing is that if you look at the throughput, right, with mixed precision, your throughput is actually like 8 times more than you have in the past. So that's why people love to have use GPU with less precise data type to calculate more. To deliver more throughput for machine learning applications. But there are also cases like Google's tensor processing unit, which is a dedicated hardware unit for matrix multiplication, and it only natively support 16-bit precision. And it doesn't support 32-bit. And if you have a 32-bit input, you have to convert it first. Okay, Fox, anything?
Oh, I forgot to put them out.
Okay, cool. So so there are hardware, as I mentioned that we only support this less precise data type, and you will never get data to be as precise as those hardware. So if you design a hardware use this less precise data types, you are definitely going to not be able to accommodate data types that require more precision. And so because we really want to get to the sequential circuits for today, so because your lab will require that, so let's keep a few things in which I think they are more trivial. So let's let's dig into the another topic. So far we are done with most of the stuff that I want to talk about, the combinational circuits, and everything include today's lecture, and the next lecture will be included in your midterm. So even though those floating point examples that I put, they are not on the textbook, but they will be tested. Okay, so so first of all, right, prior to this, right, in the very beginning of the quarter, I have been talking about there are 2 main types of circuits. One is combinational circuits, and the other is sequential logic. And the biggest difference is that for combinational logic, it's a pure function of its current input, and we don't keep the current state, and the output doesn't change regardless how many times the logic is triggered. Idempotent. That's the idempotent. That's the property that a combinational logic would own. And for sequential logic, the output depends not only on the current input, but also previous inputs and their history. So sequential circuits, they are some kind of circuits that has memory. And we also talk about the theory behind it. So for combinational logic is the theory that we are using is Boolean algebra. But for sequential logic is an implementation of finite state machine. So if you learned computational complexity or computational theory, this kind of class, I don't know what's the title in our CS curriculum, you should have an idea, okay, there is something called finite state machine. Right, so that's the theory behind it. And for Boolean algebra, there is a special class called discrete math, which you should learn in the past regarding how it works. So, so far, right, we have been spending about like 4.5 weeks in talking about the combinational logic, and it's a time for us to look around another type of big category of the sequential logic that's called that would use finite state machine. So let me start by an example. So there, you guys must be familiar with this. You saw this a lot in our opening video. In every time when I ask you a question, this is a countdown timer. So when you have a countdown timer, every second the number is going to decrease, right? So for this countdown timer, what do we need to implement this timer? So first of all, you need an initial value in a state of the timer, right? So for the example that I just showed, the initial value, the state is definitely like 10 seconds. And every second you need to signal your design with something. And this design would change its state every time when we receive the signal, right? So that's the design of the countdown timer. So given that, right, if you want to draw a finite state machine to represent that countdown timer, it starts with 10 seconds. After we receive a signal, it goes to 9. Another signal goes to 8, 7, 6, 5, 4, 3, 2, 1. Until we reach 0, then we would never decrease. So, and if you want to give the countdown timer a little bit more functions, you can set up a reset feature, which would go back to the initial states. But this lithograph is actually a representation of finite state machine of the sequential circuit. So right now you captured the rough idea of finite state machines is that it's a collection of a set of states, a set of inputs, and a set of outputs. And a finite state machine should have an initial state and a set of transitions. So you can definitely represent a finite state machine like a state diagram, which I show here, or using a state table that describe your state transition. Like if I'm currently at 10, if I receive a 1, it should go to the next state as 9. And if it's 0, I should stay the same. So that's the representation of a finite state machine, right? So right now, let's practice a little bit, right? So the reason why I'm playing Flying to the Moon, because the question is called Life on Mars. So why don't you spend some time telling me what do you think about how many states for you to implement life on the Mars? All right, we just launched the poll on Zoom now, so you should be able to click it. All right, let's wrap up in 15 seconds. Five, 4, 3, 2, 1. Time is up. Okay, so according to the poll result, most of you think, well, actually 67% of you think it's C. So first of all, can I have somebody raise your hand to explain why you think it's C? Can I have somebody? Or do we have somebody know why this question is related to the song Fly Me to the Moon? Okay, I have no friends. Okay, so okay, I have Xie Xiangying. Okay, which question do you want to answer?
Oh, wait, what are the two questions?
Okay, do you know why it is related to Fly Me to the Moon?
Not exactly. Oh.
Okay, so if you listen carefully about the lyrics, there's actually like it's fly me to the moon and let me play among the stars. Let me see what spring is like on Jupiter and Mars. That's the reason why. Okay. Okay, so but what do you, so how about the question itself? Which one do you pick?
I picked C because so because like the switching between the states basically depends on.
Okay, so for this question, right, what pattern do we want to identify? What pattern do we want to identify?
Oh, I want to see if the life detect life, basically.
Yeah, but what's the pattern we are looking for?
Oh, 001.
001. So is 001 sufficient enough to be captured by two states?
No.
Right. So the answer would be C, right? You need more than two states because you need to have a state representing we are at 1, 0, we are at 2, 0, you finally detected 1. So 3 is the minimum.
Oh,
Get it?
Yeah, because the thing is like read it as like it's like binary input X is like X is like 1 bit.
Yeah, it's 1 bit, but every time you receive 1 bit and you have to aggregate it, see how many zeros we get, and until you reach a 1, right? So that's the state transition should look like. Okay, Fanzo, anything to add?
Hello? Hello?
Hello.
Oh yeah, right. Is this a finite state machine?
I'm asking about like how many states in a finite state machine we need.
But I don't think a finite state machine is needed here, though.
No, we need a finite state machine here. Why don't you need a finite state machine? Because you are receiving 1 bit at a time.
Oh, 1 bit at a time. Okay. Oh, all right. I see.
Yeah, that's a sequence, right? That's a sequence.
Okay. Oh, I get it. So it's
right?
not like 3 bits input at the same time, but it's
No. So you need
all right.
3 states.
Right.
All right. Okay. Okay. Michael Fox, question.
The use of the word sequence as well as the use of time as the index for X and Y was supposed to be the Q, where T is the current time and T minus 2 is 2 clock cycles ago.
Right. So that's why you need more than 1 states. Okay. All right. So apparently we need more study on the finite state machine. So if you haven't paid attention to the context, we definitely have more things to learn from the finite state machine, and pay attention to the next lecture. And you will need it in your in your lab for sure. So here are a few things. We have lab 3, which is not related to this lecture. We'll do this Thursday. And for midterm, it's on next Thursday during the lecture time, access through iLearn. No less submission. Make sure that you will be able to take the exam at that time. So, so no excuse. I already told you 2 weeks ago. So you should be able to get sufficient amount of time to rearrange everything that you have, right? And it covers. Okay, so Saha's question.
Yeah, quick question about the midterm. Will we need to be on the Zoom call for that, or do we just take it separately?
No, you just take it.
Okay, thank you.
Okay, so more detail will be revealed in the midterm review next Tuesday. And how some of you were asking about, like, are we going to have what kind of format do we have? Is there going to be a sample midterm? It will all be on next Tuesday. Don't try to ask me anything about that on Piazza anymore or through email. It will be all the detail that you are curious about will be revealed on next Tuesday. And here is the set of chapters you have to be prepared for. Is chapter 1 to 3.1 to 3.12, chapter 3.15 and 16, and chapter 4.1 to 4.9. And lab 4 is up, but it's due after final. So it's relying on the context from today and Thursday's lecture, apparently the sequential circuits. So so if you are not comfortable about like starting it without learning it, just feel free to postpone it. And finally, check your grades on iLearn. We have the 1 week regrading policy.